Hello, and welcome to Lesson 9 of this Introduction to Differential Equations with Wolfram U. This lesson will introduce second-order differential equations. We will also discuss the method of solving linear, homogeneous second-order differential equations with constant coefficients using the characteristic equation. Before we get started, let's take a look at an overview of this lesson. First-order differential equations have been the topic of the first part of this course. These types of equations can be used to describe many natural phenomena, and the theory of solving such equations is highly developed. However, some physical situations require the use of higher-order differential equations. This lesson will introduce second-order differential equations, which takes the form given here, where the left-hand side is the second derivative of the dependent variable, and the right-hand side is a function containing terms involving the independent variable, the dependent variable, and derivatives of the dependent variable. Once we introduce second-order equations, we will move on to discuss classifying such equations as linear and homogeneous. Finally, we will examine a method of solving second-order equations using the characteristic equation. The general form for a second-order differential equation is given here. When the equation can be written in this form, where the dependent variable and all of its derivative terms are only multiplied by functions of the independent variable, the equation is said to be linear. When the equation cannot be written in that form, it is said to be nonlinear. For example, this equation is nonlinear for two reasons. One, the second derivative term is raised to the fourth power, and two, the y of t term and its derivative are multiplied together. A second-order linear differential equation is said to be homogeneous when the equation is in the form given here. In other words, an equation is homogeneous when the g of t term equals 0 for all t. When the g of t term is non-zero, the equation is said to be non-homogeneous. For example, this first equation is nonlinear, non-homogeneous second-order differential equation, while the second equation is a linear, non-homogeneous second-order differential equation. The function g of t is sometimes called the non-homogeneous term and adds an additional level of difficulty when solving the equation. The discussion of the rest of this lesson will focus on linear, homogeneous, second-order differential equations with constant coefficients. In this equation, the coefficients of a, b, and c are all constants. When the coefficients are not constant, the equation becomes much more difficult to solve. We will leave a proper treatment of the latter case for a later lesson. Before we examine how to solve second-order homogeneous equations with constant coefficients in general, we will consider a specific example with a familiar solution. Let's solve this linear homogeneous second-order differential equation with constant coefficients. In this case, the constant a equals 1, c equals -1, while b equals 0. The equation is subject to the initial condition that the function equals 1 at x equals 0, and the first derivative equals 2 at x equals 0. By looking at the equation, we can see that we are searching for a function whose second derivative is equal to the function itself. One such function is e to the x. Another function which satisfies this property but may not be as obvious is e to the minus x. We have seen that e to the x and e to the minus x are both solutions to the differential equation. In fact, any constant multiple of these functions is also a solution. It is also true that the sum of these functions is a solution as well. Once you discover that there are two different solutions to a differential equation, e to the x and e to the minus x in this case, then any constant combination of these functions is also a solution. This constant combination of functions is called a linear combination. Now that we have found the general solution to the differential equation, we can find the value of the constants by using the initial conditions. As a reminder, these are the initial conditions, with the general solution given by this. Using the initial condition that the function equals 1 at x equals 0, we get one equation. The condition that the first derivative of the solution equals 2 at x equals 0 gives us a second equation. These two equations can easily be solved for the constants using the Wolfram language function solve. The solution to the initial value problem is found by substituting the constants we just found into the general solution. Now that we have a solution, let's verify this solution to confirm that it is correct. First, confirm the condition that the solution equals 1 at x equals 0. Next, confirm that the first derivative at x equals 0 is equal to 2. Finally, verify that the solution satisfies the differential equation. We can see that the solution we found satisfies the differential equation and the initial conditions. Comparing the answer we found to the one returned by dsolve value, we see that the two solutions are identical. Consider this second-order homogeneous differential equation with constant coefficients. Let's assume that the answer is of the form e to the lambda t for some constant lambda. When you substitute this function into the differential equation, we get this. Factor out the e to the lambda t term to simplify the equation a little bit. Since the e to the lambda t term is non-zero for any lambda in t, we see that the equation will only equal 0 if the term in the parentheses is equal to 0. This term is called the characteristic equation. When lambda is a solution to the characteristic equation derived on the previous slide, then y of t equals e to the lambda t will be a solution to the differential equation. Since the characteristic equation is a quadratic equation, we can have either two unique solutions, repeated solutions, or complex solutions. We will first consider equations where the characteristic equation has two unique solutions. Let's solve this linear homogeneous second-order differential equation with constant coefficients. First, assume the answer is of the form y of t equals e to the lambda t for some constant lambda. Substitute this form into the differential equation to obtain this result. Factoring out the e to the lambda t term, we find this to be the characteristic equation. Now that we have the characteristic equation, use solve to find the values for lambda which solves this equation. We can see that when lambda equals -2 or -1, e to the lambda t will solve the equation. Therefore, the solutions must be this, as well as this. It is easy to show that these two functions satisfy the differential equation. The general solution is any linear combination of these two solutions. Now that we have the general solution, substitute it back into the differential equation to verify that the linear combination also satisfies the equation. Apply the Wolfram language function simplify to explicitly show that the solution satisfies the equation. Compare the result we found with dsolve value. We can see that the result we found agrees with the result from dsolve value. Let's solve this linear homogeneous second-order differential equation with constant coefficients. We can identify the characteristic equation by looking at the coefficients of the differential equation. Now that we have the characteristic equation, solve it to find the values for lambda. Write the general solution as a linear combination of the two exponential solutions for each value of lambda. All that is left to do now is use the initial conditions to find the value for the constants. Use the initial conditions to write a system of two equations involving the two constants. We can then use solve to find the values for C1 and C2. With the values for the constants obtained, substitute them into the differential equation to find the solution for this initial value problem. Compare the result with dsolve value. It can be seen that the two solutions are indeed identical. This lesson introduced second-order differential equations with take the general form here. In this lesson, we solved linear, homogeneous, second-order differential equations with constant coefficients and non-repeating roots. These equations can be solved by examining the associated characteristic equation. The solution of these equations takes the form of y of t equals e to the lambda t, where lambda is a root to the characteristic equation associated with the differential equation.